Imagine a glowing snowball of ice racing through space, suddenly growing a huge shining tail longer than the distance from Earth to the Moon. What is that thing made of, and could it ever reach us? Stay with me, we'll pull this comet apart. In this video, you'll learn what a comet's coma really is, why it has different tails, and how those tails can stretch for millions of kilometers. By the end, you'll be able to read a comet just by looking at it. Maybe you've seen a picture of a bright streak in the night sky and thought, cool, but what am I actually looking at? You're not alone. Comets look simple, but the physics behind that glow is wild. Let's start at the center, the nucleus. Forget shiny space rocks. A comet's nucleus is more like a dirty snowball, a few kilometers wide, made of ice, dust, and frozen gases, quietly waiting in the cold. Most of the time, that nucleus is invisible, drifting far from the sun. But as it falls inward, sunlight hits it, warms it up, and suddenly the ice starts to vaporize. That's when the coma is born. The coma is that glowing cloud around the nucleus. It's made of gas and dust escaping into space. Think of it like a fuzzy atmosphere. The comet grows temporarily thousands of kilometers wide. Here's the crazy part. The coma isn't just pretty, it's active. Sunlight breaks molecules apart, charges them, and makes them glow. That's why some comas look green, blue, or white in photos. Inside the coma, gas and dust are constantly flowing outward from jets on the nucleus. Picture tiny geysers of gas blasting into space, dragging dust grains with them, feeding that entire glowing cloud. Now, the coma alone is impressive, but when you add the sun's light and the solar wind, that material gets pushed back, and that's how the famous comet tails form, stretching far behind the nucleus. Important detail, a comet usually has two main tails, not one. There's the dust tail and the ion tail. They're made of different stuff, shaped by different forces, and that's why they look so different. Let's talk dust tail first. Dust grains are heavier. When they leave the coma, sunlight pushes them gently. Their path curves, so the dust tail is wide, slightly curved, and usually yellowish or whitish. That dust tail doesn't point exactly away from the sun. Instead, it bends along the comet's orbit, leaving a kind of trail. Later, Earth can pass through that trail, and we see meteor showers in our sky. The ion tail is a completely different beast. It's made of gas that's been stripped of electrons by sunlight. These charged particles feel the push of the solar wind, so they form a thin, straight tail. Because it follows the solar wind, the ion tail always points almost directly away from the sun, even if the comet is moving sideways. That's why it can look like it's pointing in a strange direction. Up close, the ion tail can be clumpy and broken. Changes in the solar wind can snap parts of it off and create kinks. Astronomers can see solar wind changes just by watching the tail's shape. So where does the tail actually start? It begins in the coma. Gas and dust drift outward, then sunlight and solar winds sort them. Heavier dust curves into one path, lighter ions are swept into another. Think of the coma as a factory, and the nucleus as the machine in the middle. The sun provides the energy, the nucleus provides the material, and the coma processes it into those spectacular tails. From far away, you can't see the solid nucleus at all. The light you see comes almost entirely from the coma and tails. The nucleus is this tiny dark core hiding inside its own glowing cloud. As the comet gets closer to the sun, the coma grows larger and brighter, and the tails lengthen. But when it moves back outward, they shrink again, and the comet slowly loses its dramatic look. Over many passes, the nucleus can run out of easy-to-evaporate ices. Then future comas and tails get weaker. Eventually, some comets become more like inactive dark rocks, almost invisible in space. Here's something fun. The coma can be so big that it would dwarf planets. Some comas are millions of kilometers wide, larger than the sun itself, even though the nucleus at the center is just a few kilometers across. From Earth, though, we mostly see the brightest inner coma and the part of the tails facing us. Long exposures make those features stand out, turning the comet into a shining brushstroke across the sky. Astronomers use different filters to isolate parts of the coma. By looking at specific colors of light, they can tell which gases are present and how fast material is escaping from the nucleus. We can also measure how fast the coma expands. By tracking how far it has drifted from the nucleus over time, scientists estimate how much material the comet is losing every second. The ion tail even acts like a natural space probe. When it bends or breaks, that tells us the solar wind has changed. So a comet isn't just pretty, it's a detector flying through the sun's magnetic field. Next time you see a comet image, try this. First, find the coma around the center. Then look for the thin, straight ion tail and the broader, curved dust tail. Suddenly, the picture becomes a story. You now know that the coma is a temporary atmosphere. The dust and ion tails are sorted by sunlight and solar wind, and the tiny nucleus is the engine behind it all. That's the anatomy of a comet's glow. If you want to go deeper into comets, and even how they might have brought water and organic molecules to early Earth, check out my next video. Hit subscribe, and let's keep exploring the space between the stars.